temp zones you're on. But right now, here I am in England. It's below 10 degrees centigrade, fall, and we're moving rapidly towards winter. So that's the time of year I like. It's wood log fires, nice and comely. So let's start talking about well integrity in the operate phase. This is quite an interesting subject. It's involved in my very first job that I ever did in the oil industry was in well integrity, and that was 45 years ago. And I've been practicing it on and off for a long time, and it is a thoroughly enjoyable subject. I find it very, very interesting. The developments keep on changing, and more we're getting into what we do as crime scene detectives. But a lot of our work involves understanding the nature of the problem. And once we start to understand it and diagnose it, we can then look for the process of mitigating the problem and complying with company regulations or the state regulations. So let me move on. So, well integrity, it really is modern day forensic science. We're crime scene detectives, we're collecting data. The more data we collect, the easier it is to help us diagnose. So, getting people at the well sites to either manually or automatically collect data and then interrogate it is the one answer to getting things right. It really, really helps. The more data, the better it is. One of the things that I work with is we can always get rid of data if we've got too much. If we don't have it, we can do nothing more. Too late, gone. And part of what I want to talk about is that well integrity is not something just in the operate phase. It actually starts right at the beginning of the well life cycle. And here we have this is a drawing that I created for the ISO standard, which I was very fortunate to be one of 14 people who wrote that, the first standard that had ever been written. And it begins in the design phase. It goes right the way through the well life cycle. So we've got the base design, the design phase, we go into the operate phase. Quite often we have interventions, and then ultimately we have to go through to the abandonment phase. Well integrity fits each and every one of those steps. It's an important element that we can't do without. So what we have, though, is a system where integrity is all about barriers. People quite often just think about barriers as being two barriers, yeah? Primary barrier and secondary barrier. But in reality, our process involves a lot more things. It involves 4 barriers, and here they are. Let's talk about these. So the first one here is we have what's called the hardware barriers, and these are the primary and secondary barriers. It's equipment which is designed, installed, and verified. And periodically, it needs to be re-verified as to its ability to withstand the pressure and the temperature that it was designed for. Moving on, we then have the operational barriers. This is the monitoring equipment, the practices and procedures. So this is pressure gauges and how often you should go out and do pressure tests, the process that you should follow. Are you sure? Okay, all right then. So I apologize for that, but I didn't realize that the voice was low. Most people complain that I'm too loud. So anyway, so then we have the operational barriers, which I've just described, and let's move on to the third barrier. So that's the human barriers. That's all about you. That's the people who are working on the well site, whether it's onshore or offshore or subsea. It's about collecting that data. It's about having the right levels of competency and training. It's no good just collecting a pressure data point and throwing it into the people. You need to be able to say it's a good data. And then finally, we have what's called the administrative barriers, the assignment of roles, resources, and the procedures that go with it. So those 4 elements all make up barriers. Now, moving on to that, let's actually talk about what the 2-barrier principle is. So what we have is a primary barrier, and then we have a secondary barrier. So the primary barrier, the blue, you have here, always sees the pressure. It doesn't matter what you do, whatever the pressure is in the well, it always sees it. And the second barrier, the red barrier, is our last line of defense. That is the one that's also capable of withstanding the same pressure. Now, broadly speaking, what we do not have is a third or a fourth barrier. Yes, they are other strings of casing and pipe in the ground, but they are primarily there to support the well. They are not there to withstand pressure. They may withstand some pressure, but don't bank on it. Occasionally there is a third barrier, and that can be put in at gases, when the gases plays are artificial liquid. So the important thing is to think about it a slightly different way, which is what's called the hat over hat principle. And you can see that depicted there with the blue and the red hats over the well. And this is developed by a Norwegian colleague and has been adopted by Norsoc, and a lot of other companies around the world use it. And it forms a common understanding about how a well is managed. So you need to have your two barriers in working order, a primary barrier and a secondary barrier. Now, what I want to talk about also is moving on to how welling texture has developed over the years. And this is quite important because there are lots of things that we do now that we couldn't do some years ago. And key elements will be shown on this series of slides. In the next few slides I'm going to show. And I divide those up into four different elements. There's standards of recommended practices, significant technical advancement, data sharing, and industry failure. So let's move on. So here we have. So the important thing here is look at the red area on the bottom half of the graph. These are red, and it's the industry failures. These are the big things that have gone wrong. It's not everything that's gone wrong, it's the big things. And regrettably, it quite often takes the failures for us as an industry to change. And I think some very, very poor or sad failures that have gone on into the life of the oil fields. So let's have a look at what's been going on. This is the past. So in 1963, Vallourec created something called the Van thread. And that was the very first gas type thread that ever came about. Before that, we had the buttress, 8-round, a variety of different threads. None of them were machined and designed to be gas type. So that radically changed our business process, because all of a sudden we had gas type threads, we needed to make them up, and they would withstand the pressure and temperature that were being put in by the reservoir formation. Now then, if we move on a wee bit in time, we had in 1973 the first extensive corrosion-resistant alloy that was created. That was 13 foam tubing. So now what we have from 1973 onwards, we have gas type threads and we have foam tubing. So that would then help us in our desire to have wells which are working better and under control controlled processes. 1972, as a result of the Santa Barbara catastrophe in 1969 and 1972, the surface controlled subsurface safety valve was patented. And that came about because the government in the US, the federal government, turned around with a massive oil spill and said, no more, we need to have a valve that works. Now, it took quite a few years to get the valve working, and in that process, we had API working on the acceptance criteria for the subsurface safety valve, but it was the process that was in place. It worked now really quite well. Then what we had in 1975 was the National Association of Corrosion Engineers, and they produced this document, MRO 175. They produced this to help us design our wells with better corrosion-resistant steels. So this helped us if we were able to write down the criteria that we have for the reservoir production fluids. NACE helped us to decide what the steel grade should be. So moving up from that, we then had, as a result of the Ekofisk disaster, Norsoc was published. This is the Norwegians put their heads together and they came up with a standard called Norsoc 30NO. And that's been working very well since, and on a periodic basis, they update that. We had a database that was started in 1988, that was reliability. So that started to get us to put our heads together to see, well, how long does a valve last? How long does a steel last? How long do these different components actually work for before we should start thinking about replacing them? It's now been superseded with other software on the market, which is very, very up to date. And that helps us now in our specification of the right parts for the right environment. But then this big thing came out as the subsurface safety cover kept on leaking and lots of problems. How do we define the leak? And this came about through a study that was put together by the Southwest Research Institute, funded by major oil companies. And this document, it is a very, very large document, certainly the subject of PhD. This document is where we come up with our 15 standard cubic feet a minute. Now, what started to happen was the oil industry started to realize that we've actually got drillers and assistant drillers and roughnecks. They're doing a variety of things on the rig floor. We need to make sure that they're competent in what they do. So in 1992, the International Well Control Forum was established, and they put together a series of tests and checks to make sure that the drilling crews were able to perform their jobs in a more safe manner. We regrettably had in 1988 the Piper Alpha disaster. As a result of that, and about a huge number of people were killed. The Cullen inquiry brought about a number of recommendations, and they were translated into a document published in 1996 called the Design and Construction Regulations 96. And this sets out the regulatory environment for the UK and how we must follow a code of conduct and regulatory processes to make sure our wells are safe. But what then came about in 1998, IWCF could see that there was a gap in the training, and this was for the pressure control. So this was for the slickline crews, the core tubing crews. Anyone who's rigging up on a well, we needed to start making sure that they knew what they were doing. Now, the SPE lesson, they were able to pick up on all the changes that were going on in the industry. And in 2005, we started with a presentation get together in The Hague. And that was where the first SPE involvement in this process started. It's been continuing most years since, and in various different parts of the world. So the SPE puts together a meeting. It's normally over 2 days. And I'm going to applaud it. It is very, very well worth attending because some excellent presentations are made and it's very, very focused on well integrity in the operating phase. Now, what curiously happened is, and this started a few days before the Macondo Deepwater Horizon accident, myself and 13 other colleagues, we were asked to start writing the ISO production well integrity standard. So we started that just a matter of days before the Deepwater Horizon disaster. As a result of that, we then had a variety of other different regulatory environments, looked at all their issues, and they were stimulated by what was going on with the SPE and many other industry practices. So we started to see things like the oil and gas UK well life cycle. NORSOC was getting updated on a regular basis. API 6A was produced, and on it went. As a result of issues around the world, particularly gas storage, whether gas storage in salt caverns or gas storage in heterogeneous reservoirs, API launched 2 new recommended practices to cover each of those environments. And they're not an easy read, but they really set out a lot of very positive things that operators should do with their wells and their reservoirs and managing what's going on. But a lot of that was kicked off because of issues that were going on in the US, and that principally was the Aliso Canyon disaster, which happened in 2015. And that is, again, quite an interesting story, well worth a read. So this carries on, so this is the future. So we have API 65-3. So that was the first, and it is still the first practice that was put together by the SPE API 65-3, and that's the recommended practices for plugging and abandoning wells. Now let's start looking at what else is going to happen in the future. So what do I think is going to happen? Well, we're going to see the ISO standard oil and gas UK, NORSOC, NOXEMA. They're going to be updated periodically. And I'm very pleased to say that colleagues in Aberdeen have recently submitted the latest updates to the ISO relatively standard. We've seen that the API are updating their recommended practices. There's going to be regulations coming out that allows for understanding or better understanding of bismuth in resins. We're going to have tougher regulations on all emissions. There's a lot going on in that environment. The disposal of carbon dioxide is a very, very big subject. The SPE have picked up on this. There's been a lot of presentations going on, but I think that's going to be quite an interesting learning curve. On the negative side, I think we're going to see some issues with the repurposing of old wells. We're going to see those being used for various different things, but there's going to be failures in there. We're getting huge problems with cyber attacks. There's all kinds of things going on there, all kinds of data or thefts going on, corruption of data and causing lots of problems. We're going to be looking at, we've seen post-abandonment leaks of wells. And what we have to recognise is that there's going to be a huge knowledge loss due to retirement, cutbacks, oil prices. The industry is changing quite dramatically. So as we move on, what we have to understand is why have we got these problems? If we have a quick review of geology, that will help us understand what is going on with these wells and why we're having problems. And if you think about it, if we look at that first slide there, what we have is the world of nature created. And this is the series of rocks and reservoirs that were in the ground, and someone very clever decided, let's drill here, that's where we're going to find hydrocarbons. So big oil, they design their wells, and they look at by design something like this. And then we move on from that. And big oil construct their wells in a certain way to comply with various different standards, to various different structures, pressures and temperatures. But the problem is that the well that's constructed has to manage pressures and temperatures. And as we see here from the arrows, a lot of things change. We start seeing pressures and temperatures in all kinds of different places where we shouldn't be seeing these things apart from expansion. And this is where we, as well integrity specialists or well integrity engineers, this is where our job continues. So we've got the well design, and now we look at how we're going to have to manage the pressure and temperature. And that's a lot of things covered there. There's lots of API documents that we can refer to. There's lots of SPE papers, all kinds of things that help us out with our understanding of these problems. But what we now need to really understand is where does our job start and where does it end? For us, that's actually quite clear. It actually starts the mill shield or perforated of the well, and it continues to the production ring valve or an associated flange at the surface. It does not, should not, and cannot go past that. Why? Because that has to be someone else's responsibility. All the pipe work. Once those pressures have been bled off and they go into a much more benign environment in the pipeline system at the surface, that has to become the area where the production and operations people manage the well or manage the pipework system. We have to have a restricted area that limits our workload. So what we now need to consider then is, what if we're working in the well integrity management system life cycle? Hopefully, there's a whole package of data that's been collected. And as we can see from this picture and or from this picture, they're both very, very similar because they're both collecting very much the same data. So what we're trying to do is to collect data at the well sites or the intervention sites, and it's going through or from those data sources to the HQ. It's going hopefully into a software package, and what the software is doing, and there's probably 8, 9, 10 different software packages that are available right now. We are constantly comparing our well construction data with our well operations data. And it's relatively simple to understand that because the well operations data must fit in the well construction envelope it's built. If it's not, we've got a problem. Outside that envelope, we've got a problem. We have a leak, something is going wrong. And this is where alarm bells should be going off. And that's how we set up our software to help trigger and tell us what's going on. So moving on from that, what we need to consider is the data part. What I'm trying to do here is to actually make it simple to understand of what we're doing and why we're doing it. So as you can see, we have this well register. This covers all our wells with a subsea, platform, onshore, and in some cases, We want to know as an operator, we might have a partnership with another operator, what is our non-operated assets, what do they do? We've got the same data package that we've got the well construction data, and we've got the well handover data. This is the package data, the as-built design by the drilling department. And that's all looked after by the RIMS manager, the well integrity management system. And we have this boundary, this line that allows people to peek inside and see data, but does not allow many people to change that data. They might be able to add to it, but they can't change the data. As a result of that, what we're able to do is to automatically generate a package of reports. So the RIMS user can look at it. We can have those different stakeholders looking at it. We might have some partners looking at it. We have all our different company standards which are referred to in the package. And these have sort of lookup tables that go back to the different criteria that we designed the well with. And then, depending on the regulatory environment, and this shows what it's like in the UK and North Sea, we have the well examination process and the regulator. They want to know what we're doing. They want to know that the wells that we're working on are safe. So there's three key features to our well integrity management systems, and those are legislative. What do I have to do? That's where the regulator has told us, you must do this. We then have our responsibilities. Well, how am I going to do it? That is set out here. Again, it's relatively simple to follow from a high level view, but it could be quite detailed in terms of what we have to do. And it all comes back to our well register, our well integrity policy, our well handover process. And again, in the UK sector, we have to have a well examination scheme. And then finally, we have the data management focus. How do I collect and present my data, and how do I then provide status reports? The beauty of the software package is that largely we can take the data and present it in a very, very visual basis that allows pictures, graphs, plots to be shown of what's going on and how it measures up with what we've set our standards to. So if we move on from this, what we have now is so we have some example regulatory documents, ISO standard, guidelines for abandonment, oil and gas UK, NORSOC DO10, and on it goes. And we then have more regulatory braiding head pressure management or sustained casing pressure. There's lots of things that's around or documents that are around to help us. But what you should be doing as a company is buying these documents from regulatory bodies, not going searching on the websites for a copy, because you never know if you've got the most advanced copy or the most up-to-date copy. And also, it is actually a criminal offence to be when you're breaking copyright law if you're taking it from the internet. So there's a variety of different things. We've got oil and gas UK documents, very, very well written for them. And we then got the other API documents that come in. So there's API 90, so 90-1 and 90-2, that's for onshore and offshore wells. We've got API 6A, a huge document that tells us exactly how we should be specifying our valves, our Christmas trees, and our well bits. We then also have another excellent document, API 6A CRA. That's the corrosion resistant alloys. Our favourite of all, of course, is API 14B, which is the design and installation of subsurface safety valves. And put this all together, what we have now is a process which is a bit like a Swiss Army knife. So we have our well integrity toolkit. This is our WIM software, our well construction data, our master calculators, our well handover process, the well operating envelope, the risk assessments, and the anomaly process. And what this is doing for us is providing us what we call the Swiss cheese process. So by checking our wells on a regular basis and having alarms set, what it's able to do is throw up problems and say you've got a problem here, you've got a problem there. And the great thing about what we're doing is we should stop the problem becoming a nightmare. We should. Doesn't always happen. But what we do is through our different processes, we have what's called the Swiss cheese. The hole should never go all the way through. So that stops our problems becoming a major issue. I'm now getting close to the penultimate slide. What we're trying to do now then is have to very seriously consider our abandonment options. Because we have invariably spoiled the environment, we have to put it back as it was. So the key thing is that we have to follow practices and procedures which are environmentally friendly and abandon our wells in the best possible way. And some interesting elements come out of this. And these are principally here, because what we're doing is we're putting the environment back to what it was. And well integrity is now considered to be from the cradle to the grave and in perpetuity. And we recently had a query that came up, what is in perpetuity? Ladies and gentlemen, it is the geological time. So don't spare a few dollars in putting that cement plant in place. You may have to spend a bit more money to get it right, but it has to be there in perpetuity. So that is my last slide. It concludes the talk. Do we have any questions coming up? Nico, do we have any questions anyway?